No, magnetic flux. How we had electric flux? No, the symbol will be this one. So what is the unit for magnetic flux? So we can write Tesla meter square or Webers. You should not get confused here. So they may put WB, flux of this much of Webers. Webers is a unit or Tesla meter square, either of one. So how we define this? B bar dot S bar. Flux equal to, and what is this? S bar is the effective area. This is here. So now this will be Bs cos theta. So let's take an area. So this is a unit vector I define. So let be uniform magnetic field. Let the area of cross section be L. So what is the flux linking this loop? Equal to B bar dot S bar. So Bs cos 0 Bl square. So what do you mean by flux here? The B bar is in the direction of n cap. Already what we had electric flux, no, the similar way here. Now the second situation. This n cap and B bar is in this direction. So what is the angle between them? BL square cos of 180. So this will be minus BL square. This is the magnetic flux. Why again the idea of flux is brought? Because the lines of force again. What about the lines of force? It's like some imaginary thing, no? Depending upon the strength of the magnetic field, we are going to assume them. And it's left to a student how many lines of force will assume. So to make it uniform thinking, the idea of the magnetic flux is brought here. Now if the flux is this n cap, if B bar is at an angle theta. Now what about the magnetic field if it is directed tangential to the loop? So the flux linking the loop in this case will be, so you can call flux through a loop 0 or flux linking a loop will be 0. Now what is this square one? This square one is a loop. Now what is a loop? Here it's a iron loop, better like iron frame or iron. Any of the words, frame, loop, conducting loop, different names can be used here. So like this, we define a flux here. So suppose if in a region, there's a frame, I'm keeping it here. Then magnetic field is into the plane where B bar equal to B naught x square. What about the flux linking the loop? Let L be the length and B be the breadth. How much of flux links the frame 1, 2, 3, 4? B is uniform, then what we do? B bar into area. If B is non-uniform, so what we do is we'll take elemental structure. So what is the best elemental structure here? We'll assume a rectangular strip. So let this be dx at a distance x. What is the flux linking this elemental strip? So d phi is equal to b into ds. So b is equal to b naught x square. Here ds is l dx. So b naught l x square dx. 0 to L. So this will become B naught L to power of 4 by 3. So there's a flux linking the loop or the frame, that one. Sir, positive or negative, I'll assume n cap along negative z axis. Let me assume the n cap along negative z axis here. It all depends upon n cap, how it is defined. So what is the basic method? If B linking a loop, if it is a constant at all points, flux is the field strength into area of the loop. If B is variable, then assume first elemental structure, then calculate the flux linking the elemental structure, then integrate total flux linking the loop.
Our area is B into dx, no sir.
B is missing. Okay. B into dx. No? What I made, I took a rectangular loop. No, so this will be B naught B L cube. Okay, ma, thank you. Yeah. So there's a flux linking this one. So elemental structures has to be assumed. So now different types of field will come. No? Who will produce the such field? Or you go back to the Biot-Savart law. There can be some different structure. So now if I keep a wire, long wire, now this is the long current carrying wire. So let this be A, let this be B. So what is the flux linking this particular loop? So there's a long wire. We have to calculate flux linking the loop which is kept nearby a long wire. Now how that both lines same plane, long wire and this line same plane. So in that case again we'll assume a strip. So let this be at a distance x. So flux linking this elemental strip with d phi. So d phi is equal to b into L dx. Or is b is equal to mu naught I due to long wire 2 pi x. This is L dx. So the limit should be a to a plus b. So there's a flux linking the loop. You assume, let's say, assume that n cap in the direction of b bar. So different types of fields will come and there will be keeping a loop here. No, b bar can be anything. It's not that it should be variation. So now let me take b bar, some sort of like this. B bar equal b naught r k cap, and we have here a ring where r is the where a is the radius. What is r? R is the radial distance. Now, how much of flux will link this particular ring? So it's all about, now the b bar is variable or constant. So b bar is into out of the plane. B bar is what? Directed along z axis, and magnitude increases radially from the origin. Radial distance measured from origin. Then what is the elemental structure? We can assume it. The elemental structure is what? I'll go for a circular strip. So let this be the radius r. The width of this, let it be dr. Let the flux linking let be d phi. So what is d phi is equal to b into dA. B is what? B naught r. So this will be 2 pi r dr. So 2 pi b naught r square dr. So what is the flux linking is 0 to a. So 2 pi b naught a cube by 3. So like this, we'll get different types of the field and the orientation of the loop. So you sometimes a loop may be there in space. If it is in space, how you define area vector? Cross product. Do remember math-based problems. Go back to cross product. If you know the vertices of a rectangle or square loop or a rectangle, can you calculate the area vector directly taking cross product of the sides? So if you know vertices of a rectangle, means the type of numericals in exam can be of this kind also, just based on basic vector. So somewhere if the loop, 3 dimension. Somewhere the loop is located like this. So I'll give space, no? So somewhere in a space, the loop is located in. I'll 3 dimensions should appear, no? It appears. Somewhere definitely it is in space. It is not parallel to. Oh, yeah. Then okay. Is it parallel to X or which plane? Nothing, no? There's nothing called a parallel. So now let this be the A, B, C, D. I'll give the coordinates of that. And I'll give the B bar. B bar equal to 2i cap plus 3j cap plus, or say minus 4k cap. Now look at the loop. I'll give the coordinates of the loop. Then can we calculate the area vector? Area vector is what, like AB bar cross BC bar. The area vector, you can take the AB bar cross BC bar, or BC bar cross CD bar. Go back to dipole moment. That you'll get area vector. Then calculate the flux B bar dot ds bar. So even if a loop is there, if it lies in some space, then how do we define area vector? So don't take a risk of finding out the area since we know coordinates. So what are the position vectors? We know position vectors. This will be the position vectors RA bar, RB bar, RC bar, and this is RD bar. So we have position vectors here, RA bar, RB bar, RC bar, and RD bar. So from the position vectors, what will happen? You can calculate AB bar. So what is AB bar? It's a vector RA bar plus AB bar minus RB bar. So therefore, what is AB bar equal to? RB bar minus RA bar. Similarly, BC bar, RB bar plus BC bar minus RC bar equals 0. So what is BC bar equal to? RC bar minus RB bar. So I know I'll give the coordinates from that, you know, RA bar, RB bar, substitute, solve it, you'll get S bar. You need not to bother, sir, angle between N bar, N cap, everything. Directly use this formula. So like that, a loop can be in a plane. So can be in a space. If it lies in a plane, very easy. If it lies in a space, you are going to take cross product. You do get some numericals of these kind. You have to be very careful about the basic maths here. Application of basic maths, nothing big.